Hello everyone and welcome to my channel. In today's video we are going to strike with a very interesting concept, that is the production of waves in strings or the generation of waves in strings. Dear students, a string, I mean to say a rope or wire or cable. So in today's video, we are going to have a deep look on how waves are generated in stretched strings. So this is my string of length L and whose linear mass density is mu. Dear friends, linear mass density explains how much mass is present in a given length. It gives an idea about the thickness of the wire. Now, the length of the wire is L and its linear mass density is mu, and it is stretched under a tension T. The following picture correctly explains about the linear mass density. Let's have a look. If you see the picture, all the wires are of same length but their thickness is not same. If you see the first wire, of course it is very thin and the mass present in a given length is less. Hence, its linear mass density is also less. If you see the second wire, it is little bit thick than first one. I mean, the mass present in the given length is more than the first one. So, it is having linear mass density more than first one. Dear students, if you see the third and fourth wire, they are much more thick as compared to the first and second. I mean, the mass present in a given length is even more as compared to the first and second. So, the third and fourth wire are having much more linear mass density as compared to the first and second. So, finally, the first wire is having least linear mass density and the last wire is having the highest linear mass density. So dear students, this is my string of length L with linear mass density mu and tension T. So if I pluck at any point on the string, mean if I make a disturbance at any point on the string, the progressive waves start traveling towards this end. These progressive waves reflects back from this rigid support and forms stationary waves. In this way, stationary waves are formed in stretched strings. The following pictures will give you a clear idea about the formation of stationary waves in stretched strings. Dear students, if you make the disturbance at any point of the wire, the progressive wave is generated. This wave travels and incidents on the rigid support. This wave gets reflected and forms stationary wave. Now we shall discuss the possible frequencies which are produced in case of a stretched string. As we have discussed in our earlier videos in case of open pipe and closed pipe. I hope you got the clarity on the formation of stationary waves in a stretched string. So let's proceed and let's have a look on first harmonic, second harmonic and third harmonic which are produced in our stretched string. To understand clearly the fundamental mode of vibration of a stretched string, here I have taken a stretched string of length L and it is stretched under a tension T. Now, if I make a disturbance at the midpoint or if I pluck it at the midpoint, the progressive waves starts traveling towards the rigid ends. These progressive waves reflects back from these ends and forms stationary waves. Now, the particles are unable to move at the rigid supports so that their displacement is zero and nodes are formed at the two rigid supports, and antinode is formed at the middle. And we know the distance between two nodes is lambda by 2 and the length of the wire is taken as capital L. So I shall equate those two so that L is equals to lambda by 2. If I try to find lambda, that lambda will be equal to twice of L. That is lambda is equals to 2L. So this is the very important equation. Now we know that V is equals to no lambda. This is the universal wave equation. Now if I try to find no, that will be equal to V by lambda, sending this lambda in the denominator of V. So this is equation star that is very useful in the upcoming derivations. Now this is the lambda is equals to 2L value. I'm going to substitute here, substituting lambda value. So in the place of this lambda, I'm going to substitute 2L from this equation. So no one, this is first harmonic or fundamental mode of vibration, that is equals to V by 2L. No one is equals to V by 2L is the fundamental frequency. So in a fundamental mode, the string vibrates with one loop with two nodes and one antinode. And dear friends, this is the first possible frequency in case of a stretched string. In second harmonic, I have taken the string with same length L. Now if I make the disturbance at the midpoint, the progressive wave starts traveling towards the rigid supports, they get reflected and they form stationary waves. In this case, instead of one loop, two loops are formed with three nodes, such that first node is formed here, the second is here and the third is here, and two antinodes are formed. One is here and the another is here. And we know the distance between two alternate nodes is lambda, so that I can equate this L and lambda. So here we have L is equals to lambda. Now from equation star, that is from wave equation, no is equals to V by lambda. Now substituting the value of lambda from this equation, so I can substitute lambda is equals to L. So in the place of lambda, I'm going to substitute L. So no 2, this is second harmonic, which is also called first overtone, that is equals to V by L. So I can multiply and divide with 2 at this time. So this is twice of V by 2L, and we already know that V by 2L is nothing but first harmonic, no 1. Now no 2 is equals to, this 2 is as it is, this V by 2L is replaced with no 1, so that we are going to have no 2 is equals to twice of no 1, mean the second harmonic is double of first harmonic. So in the second harmonic, the string vibrates with two loops with three nodes and two antinodes, as it is indicated here in this diagram. And dear students, this is the next possible frequency in case of a stretched string. Now, to observe the third harmonic, I have taken the same string with same length capital L. Now, if I make the disturbance at the midpoint of the string, the progressive wave starts traveling towards the rigid support. Again they reflect back and form stationary wave. In this case, 4 nodes are formed. The first is here, second is here, third is here, and the last one is here. And 3 antinodes are formed, 1, 2 and 3. Now, in this case, the wavelength is written as 3 lambda by 2. As we know, the distance between two alternate nodes is lambda, and the distance between two successive nodes is lambda by 2. So this is 1 and this is half. So 1 plus half is 3 and half, that is 3 lambda by 2. So this must be equal to the length of the wire. So I shall equate those two. Here L is equals to 3 lambda by 2. Now if I try to find lambda, this 3 by 2 goes that side and becomes 2 by 3. So that lambda is equals to 2L by 3. This is the very important equation which is to be substituted in further derivation. Now from equation star, that is from our wave equation, we have nu is equals to V by lambda. Now we can substitute the value of lambda, that is nu 3 is equals to V by 2L by 3. This 2L by 3 is substituted from this equation in the place of lambda. So in the place of lambda, we are going to substitute 2L by 3. So this 3 comes to the numerator. So nu 3 is equals to 3 times V by 2L. And as we know, V by 2L can be replaced with nu 1 as this is the first harmonic. So nu 3 is equals to 3 times of nu 1, which explains that the third harmonic is 3 times more than the first harmonic. So in the third harmonic, the string vibrates with 3 loops, with 4 nodes and 3 antinodes. And this is the next possible frequency in case of stretched string. Dear students, this is a very crucial moment because now we are going to have an overall look of the picture. In the first harmonic, the string vibrates with 1 loop with frequency value 1 times of V by 2L. In the second harmonic, the string vibrates with 2 loops with frequency value twice of V by 2L, nothing but 2 times of V by 2L. In the similar manner, in the third harmonic, the string vibrates with 3 loops with frequency value 3 times of V by 2L. So if I write all the frequencies in a single equation, I'm going to have nu 1 is to nu 2 is to nu 3 is equals to 1 times of V by 12 is to 2 times of V by 12 is to 3 times of V by 12. So I can cancel all the common terms so that I will be having 1 is to 2 is to 3 is the frequency ratio for my stretched string. Dear students, thank you so much for your cooperation, and our videos are waiting for your comments. So if you like our videos, please let us know in the comment section. And thank you once again.